Alright, so like the last video when we looked at examples of normal forces and looked at normal forces scenarios, this one we're going to look at scenarios where there's tension forces, and there's going to be 4 of them that we're going to look at specifically. So let's start with case number 1. So here we go, starting with number 1. We're looking at the vertical tension forces on a static object. So we're going to start really simple, right? So what we're looking at is specifically this type of object or this type of diagram, where this is like a cord or rope, a type of cord, right, or a rope. And if you recall that ropes and cords, all those, these are related to tension forces, right? So let's think about that. Let's draw the free body diagram right here. The free body diagram is not too bad, right? We have a tension force going upwards, and then we have the weight of the object going downwards, right? I'm going to use capital T for my tension forces. I don't know if you use a different symbol, that should be fine. But I'm going to use capital T. And this one's pretty easy. We'll want to use Newton's second law in the y axis, right? And it's not moving, which is always helpful. In other words, T minus mg is equal to 0, or T equals mg. And it's very similar to that very first one we did with the normal one, where it's kind of just like a very simple statement where the tension is just the same as the weight. So on to the next one. Now we have vertical tension forces on an accelerating object, and it's kind of very similar to our second case with the normal, where we have it, if you imagine it on a elevator, right? But this time the elevator is going downwards. So we're going to think about that instead. So we have, as always, our free body diagram. We have a tension, and then we have a weight. Tension and weight. So now you want to plug it into Newton's second law, right? Sum all the forces in the y component, and it's equal to ma. I'm going to specifically, now since acceleration is pointing downwards, I'm going to actually make this way the positive direction. Usually I like to make my positive directions the same direction as acceleration, and it just helps me in the long run. So in fact, then this makes this one a positive thing, and this one's a negative force. So mg minus t, the tension force, is equal to ma. And then I'll probably just solve for t, so t is equal to mg minus ma. In other words, t is, let me write it in purple actually. So in other words, t is mg minus a. So kind of like very similar to the normal force application, but the only difference here is there's kind of actually the same. If I were to substitute n here and then place the block right here, it'd actually be the same kind of equation. But this is just dealing with tension forces, and notice that since acceleration is pointing down, and we end up seeing a negative sign or a minus sign right there instead of a positive sign. In contrast, if I were actually going upwards in acceleration, we would actually get a plus sign right here, right? You can do that yourself if you want to double check me, but we're going to move on to the next one, so let's move on. So case number 3, 2 tension forces at symmetric angles. So this is the picture that represents this scenario. So we want to actually draw a free body diagram right here. So it kind of looks like this, and then we have the weight, right? We have to give them different tensions, and then we see that this is an angle that we want. This is the angle that we are used to represent them, right? So kind of like with the normal force, normal force video, we have to break these tension forces into components. So I'm just gonna like enlarge it a little bit just to get the idea. So tension forces have in this case, we have this and we have this, right? And these are the same angles just to help us because they're symmetric angles. So we see that the ones right here are tension of whatever, right? T1 cosine, since it's adjacent to that angle. And same with this one right here, right? And then these two on the top are the opposite of that angle, so they must be T1 sine theta and T2 cosine, T2 sine theta, right? And then t2 cosine theta. So this will help us with our free body diagram even more. So let's actually redraw it just to make it more clear of what I'm talking about. So we have the weight. We have a, I guess this way is the t1 sine theta. Okay, let me go ahead and move it here. So we have this right here, and then we also have the t2 sine theta right here, and then we have two upwards, one going this way and one going this way. This is t2 cosine theta, and this is t1 cosine theta. Right, so this is the free body diagram broken up into components, and then basically we want to use Newton's second law, right? The y components here and the x components here. The block is not moving in any direction, so it's 0 on both sides, or in both equations. So the y, we have t2. I'm going to define first before I actually continue. Upwards is positive and rightwards is positive. So t2, what is this? t2 cosine plus t1 cosine equal, or not equals. Oh, I need to erase this. Minus the weight is equal to 0. In other words, we can actually we can say that these, for right now, we can actually say these are the same tension forces because they are symmetric, but it's usually helpful to separate them. But I'm going to actually combine them now. So this is actually 2 cosine theta minus mg equals 0. And we can combine them only because they are actually the same tension, because they're symmetric angles with the same block, right? But we'll look at a case where they're not the same and how to go about that. So I kind of want to solve for tension, so let's actually do that. So to do that, I have to bring this and then divide by 2 cosine theta. So in all, I get t is equal to mg over 2 cosine theta. Now let's look at the x directions. So like I said, they're the same tensions technically, so I can just rewrite it as a single t. And we see that they're actually just simply cancel each other out, so it doesn't really tell us much. And that makes sense because it's not moving horizontally at all, and we have two tension forces balancing each other out. So it makes sense that the forces all cancel to 0. And they're the same force, so that's why they cancel. So now we're going to look at the final case, which is when these two are not symmetric to each other. So here's our final example, the one that I was talking about with the non-equal angles. And you can see they're completely non-equal, right? You have one where one of the tensions, I'm going to label this tension 1, is attached to a wall, and then the other one's kind of at an angle that's attached to a ceiling, and it's just holding the mass in place like that. It's just kind of an interesting scenario, but we're actually going to apply some physics to it. So let's actually just draw the general arrows of where everything is. We have the weight here, right? We're going to have to keep track of T1 and T2 specifically because they're different tensions. And now we want to start breaking stuff up, right? The only one we have to break up is T2, so let me just enlarge that really quickly, right? So we have this, and then the angles right here, so we can break it up into this component and this component, right? So then, since this one is adjacent, it is T2 cosine, and since this one's opposite of the angle is T2 sine. After that, we should probably go back to our free body diagram and draw a better one with components. So mg, this one is T1, we have T2 cosine, and then we have T2 sine. There we go. So let's kind of scroll this down a bit if I can. There we go. So now we should use Newton's second law in the y and then the x. Let's do the y. So the y is not moving, so 0, right? So now we want to sum it. So I'm going to define this way and this way as my positive directions. So let's continue. T2 cosine minus mg is equal to, what is it equal to? It is equal to 0. oops, not data, 0. And then we get our final result. We get t2, let me solve for t2, is equal to mg divided by cosine theta. Okay? Now we want to look at the x direction. Equals, it's also not moving, right? So in this one we only have two forces as well. T2 sine theta minus T1 is equal to 0. In other words, we have two tangent forces and an angle. So we can actually do something pretty interesting here. Kind of use these two equations together. We found something in here, we can plug it into here. What we found here is this equation. We found what T2 was equal to. So if we really wanted to, we can solve, let me just solve for T1 really quickly. T1 is equal to T2 sine theta. And then we can plug in T2 right here. So let me see if I can scroll down. There we go. So what it is T1 is equal to what? Mg cosine of theta sine of theta, right? And if you see right here, this makes up a tangent. So in all, we actually get something pretty interesting. T1 is equal to mg of the tangent of that angle. And remember, that angle is right here. Right, that angle. So we can find T1 just by taking the tangent of this and knowing the weight of the object, which is kind of interesting, I would say. Same with T2, we just need to know the cosine, right? And that's pretty interesting, I find pretty interesting. So again, let's look at the whole process. So it's kind of very similar to the normal force kind of problem solving strategy, right? We have to draw the free body diagram from the diagram and then we were solving for tension in these examples rather than normal force. And we had the very basic one, right? Something stuck to a ceiling, not moving. We tried looking at an acceleration one, and then we tried looking at symmetric angles, and noticed that they're the same tension force because they're symmetric. And then we looked at this pretty interesting example of non-equal angles. And basically this general problem solving strategy can be applied to any of these types of tension problems or normal problems. You just have to get used to this problem solving strategy. I wouldn't be too bothered making sure you know every single case, but just knowing the strategy for each case, or pretty much all the cases. All the cases are basically draw the free body diagram here, right? You have your initial one. You want to take what's diagonal and break into components, redraw your free body diagram in terms of those components, and then use Newton's second law to get your kind of like two main equations, and then maybe they interact with each other like this example. And then you can plug in whatever you want for the problem that they ask you. Like what if they give you the mass of the object and the angle? You can find T2 and you can also find T1, right? But we're just trying to get a general idea and a general strategy to practice with. So we're going to continue our general strategy with the next video, doing the same thing.